Hello, my name's Callum. I'm a part of the WhosClimbing team, and today we're going to give you a demonstration of our minimum viable product, which is an application to connect across indoor and outdoor climbing locations. So in terms of the delivered functional requirements, users will be able to create an account and make friends across the world and navigate through an interactive map where mutual friendships will trigger email notifications to those involved. On the map, users may express interest in various climbing locations, while online, the user's friends will be able to see any interest on the map instantly within their browser. While offline, users have access to all functionality of the application, where events are queued and completed once back online using DEXI. The map is progressively updated and enriched with new points of interest as the user navigates around, using the geo-enriched celery worker. And the interactive map has been implemented using the Mapbox service. So in terms of non-functional requirements, scalability was delivered through AWS auto-scaling services, and this was implemented within our design using Terraform, where email and geolocation components were designed as celery workers, which can be scaled independently during seasonal periods, and these are triggered by sending them through the Redis event broker. While offline, users have access to all functionality of the application, where events are queued and completed once back online using DEXI. This allowed us to deliver offline availability to climbers who often find themselves in off-grid locations. WebSockets were used to allow two-way communication between the client and the server to partially implement instant updates on the front end, specifically through the expression of interest feature. Using OpenStreetMaps, anyone can add a location to the WhosClimbing map. Interoperability with an open source API means that our application can grow without our users having to manually add climbing locations. The map is progressively updated and enriched with new points of interest as the user navigates around, using the geo-enriched celery worker. Effectively, our app is able to benefit from people using OpenStreetMaps, which is really vital in the early stages of development and for a minimum viable product, where we won't have a heap of users using our application. The app really prioritized interoperability with board climbing apps, scalability during peak seasons, and real-time availability. However, during design, we recognize that climbers often face weak or no connectivity in remote areas, making constant real-time updates impractical. Therefore, we shifted our primary focus to availability and in the name of enabling offline use with data synchronization upon reconnecting. Additionally, our initial interoperability goal was impacted when the CRAG, our intended climbing data source, restricted API access, and the BoardLib API offered poor integration. Instead of tunneling in on statistics, we chose to integrate the OpenStreetMaps API. This was to focus on encouraging climbers to discover new areas and connect by exploring our application. The updated priorities became offline availability, into scalability, and then interoperability.
Okay, so hi, my name's Ben. I'll be talking about two ASRs today. I'll be talking about interpretability with Overpass and OpenStreetMaps, and I'll be talking about availability with offline, in the bush, access to our core features. So here we can see several points that have been pulled in from OpenStreetMaps and displayed on our application. We notice that one is missing. For keen outdoor boulders, they'll know that at Sparks Hill, it's a bouldering location. So in order to add that to our application, we go to OpenStreetMaps and you can select a new point, quick headings, and then we'll also add a sport tag. Okay, now that we've done that, we can save it. Okay, and then eventually it's registered itself in OpenStreetMaps and we can see it. You saw it pop up on my screen just now. Sparks Hill Boulder Reserve. It's now listed here. So that's how our app provides information off to Overpass and OpenStreetMaps, and how OpenStreetMaps in turn provides us with a useful service showing off interpretability. Now let's throttle our network connection to offline. Imagine we've gone out into the bush and we're using our application offline. You're now offline. So it's a progressive web app, so it has local browser caching, and users can present interest and add friends when they're offline. So I've just clicked add interest and it came up with your action was queued. Now when we change our network throttling to no throttling, you can see your changes are applied. You can see the sockets have reconnected. Our locations are again being fetched in and updated. And our interest in the location has been updated.
Hello, I'm Jason, and now I'll walk you through our mutual friend notifications feature. A goal of this email worker is to enhance the social experience by notifying users when their friends connect. This functionality relies on an asynchronous email worker. So here we have set up 3 user accounts, Jason1, Friend1, and Friend2. Currently, Friend1 is logged in, as you can see, and he is already friends with Jason, as you can see in his friend list. And now, the Friend2 account has sent the Friend1 a friend request. And because while both Friend1 and Friend2 are friends to Jason, Friend1 will now accept the friend request from Friend2. And because, as I said, because Jason is the mutual friend to both Friend1 and Friend2, he automatically receives an email letting him know that they have connected. And right this moment, a background task is triggered. So here we see an email that let Jason know that their friends have connected. And this entire process is managed by our notify mutual friends task, defined in the task.py, identifies that these mutual connections and sends the emails. We have tested this worker with our test email nodi.py script, ensuring that the notifications are sent reliably, which shows that the system's interoperability with email services. Moreover, this worker also shows the scalability of our system, and now I'll pass it to Tim to talk about it.
Okay, let's look at how the system performs under stress. We use the K6 load testing framework to simulate various user scenarios, from normal data use to high traffic weekend peaks. This one shows our auto scaling in action. As the K6 tests increase the number of users, our infrastructure automatically creates more API tests to handle the load, scaling from 2 total tests up to 9. This demonstrates that our MVP is elastic and can respond to real-world demand. This slide shows the final results of the test, which ran for over 17 minutes. Our login success rate remained high at 98.3%, and the overall check success rate was also 98.35%, which we believe is acceptable for the MVP. We hit a peak of 9,700 total requests, averaging over 9 requests per second. Despite this heavy load, the average request duration was kept under 9 milliseconds.
WhosClimbing leverages an event-driven architecture to effectively address both functional and non-functional requirements of our climbing application. At the core, our system employs 3 main components: producers, a broker, and consumers. Here we see the front-end component diagram. So producers, represented by our progressive web app, front end capture user interactions. Users can seamlessly interact with the app online or offline, queuing actions locally using Dexy, which manages local storage and synchronization. This design ensures robust availability, crucial for climbers in remote areas without internet access. Our front end employs a model view controller MVC structure tailored for progressive web applications. The model uses Dexy for client-side caching. The view is implemented with React, and the controller manages client-side business logic and pre-processing, significantly enhancing offline capabilities and responsiveness. The use of WebSockets implements real-time updates essential for modern, socially interactive applications. Although real-time responsiveness was revised as a requirement for the MVP, incorporating WebSockets is still valuable as it delivers our initial vision of availability to provide an application which felt alive. Any actions, offline or online, are sent to our backend API, which translates them into system-wide events and forwards them to the reader's broker. The reader's broker reliably queues and dispatches these events to asynchronously running workers, the geo-enriched worker and the mailer worker. These workers encapsulate tasks that that are computationally intensive or dependent on external APIs, such as fetching geospatial information, weather updates, or geological data. By decoupling workers, we achieve high scalability. During seasonal peak periods, we can scale individual workers independently, ensuring the system remains responsive and performant. Our architecture simplifies integration with external APIs like OpenStreetMap for climbing locations, Geoscience Australia for geological data, and weather service. This modularity ensures interoperability, where users experience seamless integration with familiar external climbing services, fulfilling a critical functional requirement for the MVP. Additionally, the architecture supports immediate notifications via the mailer worker, maintaining user engagement through real-time email alerts and updates using Gmail's API. WhosClimbing's event-driven modular architecture delivers robust availability, scalability, and seamless integration with external services, precisely meeting our MVP's functional and non-functional goals and providing a solid foundation for continued development.
The implementation of the WhosClimbing web app provided a number of valuable insights into the process of software architecture development. One of the biggest takeaways from this project was the benefit of an iterative build approach. In our project, the front-end development started from a basic back-end integration before implementing React with client-side rendering. We then added progressive web app capabilities with DEXY offline functionality, and finally, real-time WebSocket communication. Similarly, the backend evolved from a simple monolithic Flask application to a containerized deployment, then event-driven patterns, cloud deployment, and finally auto-scaling infrastructure. This proved highly effective in managing architectural complexity while maintaining development momentum. It also allowed us to validate core functionality at each phase while building the foundation for more sophisticated capabilities. Each iteration provided working software that could be tested and refined, rather than attempting to build the complete complex system simultaneously. Future projects would benefit from this iterative architecture approach, as it reduces development risk and allows architectural complexity to be introduced incrementally rather than all at once. Despite this success, the project also ran into several problems that could have been avoided with the right steps, each of which again provided valuable insight about designing a software system. One cause of lost time during the project was having to redesign the functionality and structure of the web app after finding out that the external API integration for the CRAG would not be possible due to the owners closing it off to non-commercial applications. This caused us to have to change our architectural decisions and find available APIs that would both be meaningful to the web app and achieve our quality attribute of interoperability. In future, we would invest more time into external API feasibility, testing, and research before committing to a specific integration, as early feasibility testing would help us avoid having to pivot late in the design or implementation phase. Finally, scope creep management was challenging in the project as our long design and redesign phases led to us discussing and trying to include a number of additional features. While some additions to the scope, like the geo-enrich and weather data, were valuable and needed due to the loss of functionality from the CRAG, other decisions led to a much more intensive development period. The move from basic location mapping to a complete offline-first architecture, for instance, represented a monumental scope expansion. However, it was determined to be valuable in achieving our availability ASR. Whilst these features made the final MVP, there were several that were discussed in length to be too far outside the scope of the MVP. These constant discussions and research into features led to a lot of wasted time. Future projects would be aided by establishing better scope limits during initial planning phases, with defined criteria for evaluating additions against the quality attributes.